Good afternoon, guys. We'll go ahead and get started with today's Innovation and Propulsions panel. We'll go ahead and quickly introduce our panelists, but the goal of this panel is mostly to open up a discussion with you guys as the crowd, with the panelists that we have, to ask any questions about emerging technologies and what we're seeing change in the marine propulsion environment. So who we have on our panels, we have Dave Lee from ABB for the electrical side. We have Tim Sassine from Ballard Power Systems to help discuss the fuel sales technology. And then myself, Joshua Sebastian at the Shearer Group, will be talking about the status of our LNG projects that we have going on currently. So there's Tim. He's joining us virtually. You'll see his video feed back up when we do the Q&A session. So I'm just going to give a quick introduction on the status of LNG and where we are at with that on the marine side. Again, I'll let Dave will go into energy storage and that aspect. So LNG as a fuel is coming to the inland rivers. We are currently working on a number of projects converting vessels right now. Ones we had talked about briefly last year during our virtual conference was the one for the SCF Marine Highway System operating in the Port Allen area. That was the one where we are using fumigation technology. And then we are currently working on a LNG conversion for a line haul, 10,000 horsepower, operating on the lower Mississippi using LNG conversions. So again, the SCF Marine Highway and the Container Express, triple screw Z drives using Cummins QSK 19s, 800 horsepower each. We're going to be putting approximately 12,000 diesel gallon equivalent of LNG storage on the vessel, and we'll be fumigating with displacing approximately 50% on average of their diesel fuel will be displaced with LNG. You know, one of the main goals is not just the fuel cost, but also to reduce the emissions. There will be an emissions study that's going to be conducted by the same group of people who found the Dieselgate with Volkswagen. So we know that we won't be able to get anything by them, but that's a part of it, is we want to see the before and after the testing. You know, one of the advantages with the fumigation system is it is a true dual fuel path, because you can run on a blend of diesel and LNG, or you can run on all diesel if for some reason that you need to, LNG is not available, or if you're under high power applications, because still on the LNG side, a lot of LNG engines can be slow to respond. So with having the diesel in there, the technology is such that if you have a rapid change in power requirements, the diesel will kick in, will be the majority of the fuel until you get to your steady state, at which point the LNG will start to get blended back into the fuel stream. Now, the challenge with the fumigation system is that the Coast Guard had adopted the international code for gas-fueled vessels, or what we call the IGF code, for all LNG vessels in the US. The LNG code, the IGF code, is not very friendly to fumigation technology. So we had to work very closely with the Coast Guard to develop equivalent level of safety and come up with an alternative set of rules that would allow us to operate within the IGF framework, but also to allow fumigation technology on board the vessels. We have gotten the approval for all that, and we are at this point going through the technical design review process with Coast Guard, focusing on the equipment, getting all the approvals for things like valves, throttle valves. There's a lot of stuff in there that is very difficult to find the right kind of safe equipment, but we have gotten through all those hurdles. We're going through the technical review. We've been getting most of our approvals back. And, you know, we expect that these vessels will be on the river operating LNG in the near future. The exciting one that we have started more recently is a 10,000 horsepower line haul that is operating with EMD 710s currently, and we're going to be changing them out. The engines aren't going to be changed out, excuse me. We're going to be using the progressive rail retrofit that are placed in the engines as part of the overhaul package of when you do an EMD. You're just, instead of doing the normal cylinder liners in the power pack, you're using their LNG, their dynamic gas blending power pack and cylinder liners that inject the LNG into the vessel. We're going to be adding about 150,000 gallons of LNG to this vessel, and we'll be able to, with the dynamic gas blending, we'll be able to displace about 70% of their diesel consumption with LNG. With that, I will turn over this portion of it and let Dave Lee discuss where diesel, electric, and hybrids are with the towboats.
Good afternoon. First thing I have to say is it's awesome to actually see people's faces when I do one of these. The past 16, 18 months, it's been quite miserable staring at my own computer screen. So it's awesome to see this. So I'm here today to kind of dovetail on what Josh started with, which is diesel, electric, hybrid towboats. Where are we today? Where are we going? The first thing, I'm an old towboat guy, as Joe's sitting here staring at me. And I do know one thing about inland guys. We don't change very fast. We put a lot of thought into what we do. The towboat design hasn't looked any different for how many years, Joe? You've been around since the first one, I think. So, but with that, as we did this conference, I tried to update our graphic to show, hey, what new and improved. And I thought about putting lightning bolts down the side of it because we're starting to talk about hybrid and battery. But the only thing I did is I put a little green light on the top of it, just to show we're not going to change all that fast. We just aren't. So with that, I always throw this up, and people probably have seen this before. Why do we even talk about this? Why? Is it something that I need? Well, these people say yes. And these people are our customers, our regulators. So first of all, we talk about IMO. That's the overall global entity that's pushing towards emission savings, right? The next is where we operate. So if we look at the operation areas, these don't change much. But they do change. And this is every discussion that I have, I always put the new one up. So Port of LA, Port of Long Beach, of course, right? Port of San Diego, of course. They have zero emission goals in port. The last conversation I had, Port of Houston, 70% carbon footprint reduction by 2040. That's big. That's where we operate. The new one that I added for this discussion is down at the bottom. Net zero carbon emissions by 2050 from the state, from the city of New Orleans. And specifically in their statement, they talked about watercraft in the port of New Orleans. So again, that's the additional one for this. But then the other one is our direct customers, Shell, BP, ExxonMobil by 2050. They have net zero emission standards, goals. Those are our customers. We're building boats today that last 30, 40, 50 years. Geez, I think I saw one in the Waterways Journal last week, 60 years old. They just got a new COI on it. They last forever. If we're building a boat today, and we're only talking about 30 years from now, we need to have these in mind when we make the decision on what we build. So with that, how do we get there? This is a whole lot of little diagrams and stuff up on the board, but it's really truly what the industry has seen as that pathway to get us to zero emission. So we have currently where we're at, LNG, energy storage, like Josh talked about, shore charging. That's a big one. We start talking about not only inland vessels, but definitely we start talking about ferry segments, vessels that operate in heavily populated municipalities. That's how we start getting emissions out of our vessels. But what we really see is what Tim's going to talk about here shortly as well is the introduction of fuel cells coming along into vessels and how quickly that's actually happening. You know, LNG is a great bridge, and Josh and I have had plenty of discussions about that, but everybody knows LNG is not the fuel 50, 60 years from now. There's going to have to be something different. And this is what we see along with the introduction of batteries, PEMS fuel cells, which Tim's going to talk about, getting all the way to solid state fuel cells. This is no different than talking about today. We're talking about lithium ion batteries. However, in 5 years, the car industry has already said 3 to 5 years, they're going to have solid state batteries. That's really when you start condensing the energy, getting down the weight, getting down the space required for these, which is one of the most important things in an inland vessel. So we see that transition already in the car industry. With that, everybody's heard me say inland, we're probably 10, maybe 15 years behind what happens on the road. It will happen here. This is a graph from the Maritime Battery Forum, and you see it's almost starting to go exponential on the number of vessels around the world that has energy storage. What's interesting in this, if you look at the numbers for 2021, it's 274 in service, 208 under construction. Just last year, that number was 246 and 195. So 1 year we had that large of a step change. And that, as you see, that's a current trend. We will see batteries in vessels on the inland side and in the harbor because you see this trend happening very quickly. As we see diesel prices increase, traditionally over the years, battery prices have started to decrease. Fuel cell prices have started to decrease, and that will continue this trend upward. I'm not going to go into this very much, but this is actually showing you what's available today in fuel cells. Currently in fuel cells, they are PEMs, proton, I'm going to lose my mind now, is a membrane system for hydrogen, okay? We have small ones on the that can be introduced currently into vessels, but one big project of working on ABB and Ballard together is this 3 megawatt containerized system. This is targeted currently for the offshore oil and gas, for the cruise industry, where it's an easy retrofit, but this type of system can easily be introduced into a larger towboat in the future. And then when I talk about future proofing, what I talked about before is we need to keep our eye on the fact we're building boats today. They're going to be here a long time past that 2050 goal from before. Long time past me being in an industry, hopefully, right, Ed? But with that, we look at this as a building block. The most important thing in this building block are these electric motors on the aft end. If you build in a typical diesel mechanical arrangement with the large diesel engines, you have the shaft line, you have all the large engine beds you're putting down, all that stuff has to come back up if fuel cells become more prevalent, if ammonia as a full fuel becomes more prevalent, on down the line. There's a lot of those ifs, but you can future-proof today by at least putting electric motors in. I can change out these diesel gen sets. Yes, you see on this one, we have hydrogen fuel cells, a hydrogen tank. Those are easy. They're skidded units. Change them out, throw a battery room in. But you have to have the electric motor in the first place. And this is why it's so important. One, you're ready for the future. Two, you get all these other benefits. And in these different power systems, we've worked with Josh on several different projects of what's the right fit. There's not a one size fits all. If you're a fleet boat, you don't have the same profile as a line haul boat that goes from New Orleans to St. Louis. Then again, you don't have the same profile as a unit towboat that could be in Houston one day and Pittsburgh the next week. You know, there's not one size fits all. So we look at this as the building block to all these systems and work with the owner on which is your best fit. But you get all these typically in that enhanced dynamic performance. Anybody who's been in a Tesla, you know that once you put your foot down, it's gone. That's the electric motor side of it. You have 100% torque at 0 speed. You're going to burn the tires off the thing. It's what you get in one of these systems. Fuel savings. I will say, and I think I said in the last discussion last year, sometimes we have to be very careful what the profile is on the boat that you're operating if it makes sense on fuel savings. It may not, but we work with the customer up front to normalize that and figure out, will you have a fuel savings on that boat? Maintenance, as you start dropping engine running hours like crazy, you could run one gen set in a diesel electric setup where you normally have to have 2 engines and a gen set running. You're really dropping those engine running hours down. Maintenance turns into direct dollars for your pocket. Redundancy, uptime, you could have a boat that has 4 gen sets in it that are redundant to each other. You don't have to shut down because of it. One of the things for Josh's side, the LNG side, we can do PTO, PTI LNG. So an LNG engine is very slow to ramp up. So where you have an electric motor on a secondary shaft on the gearbox, or we can do it in line. It takes that low power until the LNG engine ramps up, and then the electric motor backs off. That's one of our current projects in Singapore on a tug with that exact system. Spinning reserve. So if you lose a generator, if you have batteries in the system, you have immediate power there. You don't actually ever lose anything. And of course, zero emission operations. With that, this is some of the all battery projects. And as you see, it starts to leak into the inland industry. Of course, ferries. Josh is familiar with at least one of these up here. Those are much simpler to size a battery for because they're point A, point B. Again, inland towboat, who knows where the damn thing is going to be from one week to the next, right? But that's where you start seeing the Z-Tug come into the picture. That's an all-electric tug that operates in the harbor. A fleet boat would have the same type of operation for the inland side. And then with that, this is the fuel cell projects. You see the ones at the top, several of those were involved in the Golden Gate Zero operation. Peter SEM sitting back there, heavily involved. That won't be in operation this year. First fuel cell vessel in the US, 100% fuel cell operating in San Francisco. Down below, you actually see what's funny is how it leaks, this technology leaks into inland. We have the first inland fuel cell towboat in Lyon, France, hopefully later this year. Due to COVID delays, it's a little behind. But with all this, these are technologies that we're not just talking about that could happen. These are happening. And they're just not in the US at the speed that we typically see it elsewhere. So all that is to say, all these have this goal in mind. Number one, I already talked about it, needs to be electric. Needs to be. It's enabling technologies to power the world without consuming the earth. We've consumed the earth for way too long. We need a better way to do things. Things I didn't bring up is the digital side. Once you start moving electric, you really start having a much more control over all the different systems on the vessel itself and then connected. Once you have all the digital side, the brain connected into what you're doing on propulsion, then you can start operating that thing anywhere you want. You can start dialing into it anywhere you want. And those are the building blocks to future-proof the marine fleet. So with that, I'm going to hand it over to my buddy, Tim. Tim, are you there?
Yeah, I'm here. Thanks for the intro, Dave.
Of course.
Yeah, super jealous of you guys being there. And I am flying a bit blind here, but Dave has promised me to be my Vanna White, and he's choreographed some dance moves to go along with these slides. So hopefully you guys get entertained. I am Tim Chassin. I'm the Market Development Manager for Ballard Power Systems for the United States. We are the world leading manufacturer for proton exchange membrane fuel cells. And in this first slide that you should be looking at right now is a little bit of a rundown of what exactly a PEM fuel cell is. Dave alluded to it before, but there on the left, you can see a graphical representation of it. And essentially what you're doing is you're taking a gaseous fuel. We talked about natural gas earlier. In this case, it's hydrogen. And you're reacting it with oxygen, but instead of burning it to get pressure to move a piston, what you're doing is you're reacting it at a low temperature across the membrane. You're controlling that reaction. And instead of getting pressure out of it to move a piston, you're getting electricity out of it. And that's what you see in that diagram. The hydrogen comes in on the left side and it splits apart. The proton migrates across the membrane. The electron becomes your electricity that goes across your electrical circuit, your motor, and it meets up on the other side with oxygen from the air, and it creates water and it creates a little bit of heat. And that's essentially it. So essentially what you've got is a mini engine that is cold burning hydrogen, not producing NOx, not producing anything but water. And it's behaving just like a battery. What it's doing is producing electricity, and that represents what we call a unit cell. Each one of those produces about 1 volt, and you stack those up just like you stack up batteries to get the voltage you want. You make them bigger if you want more current, and that's how you get power out of the thing. The next thing over, the unit cell components, are the different pieces. It's a sandwich. Basically, you've got 2 carbon plates that guide the gases and conduct the electricity. And in the middle, you've got a thin film. It's like a Gore-Tex. It's like a Mylar film coated with platinum. So highly recyclable, and that platinum, being valuable, is also recycled as well. We recover about 97% of that when we refurbish these stacks. And they're put together in a stack. You see that in the third picture, fuel cell stacks. That makes them highly refurbishable. We can unbolt that thing, put in new membranes, wash the plates. We usually reuse them about 6 times and bolt it all back together. And those things will run for about 30,000 hours or more. We put multiple stacks into a fuel cell module. We're on our 8th generation that you can see there. That thing provides the gas flow, filters the gas, and provides electrical connection and monitoring for it. And that's what we produce at Ballard. That is a fuel cell module, and that'll go into your vehicle. We started in buses, we're going to trucks, but marine applications are a huge area where we see a whole lot of need for the stuff that we make. On the next slide, we're going to see 3 different types of fuel cell modules for different types of vehicles. And that top one is what we're putting in buses. That's our FC Velocity. Those are all over the world. We've got over 1,000 buses around the world that are running with those modules. We make them in a variety of sizes. And in fact, we're going to a new version, the FC Move, which you see there in the middle row. And that is the integrated version that brings in a lot of the balanced plants. It's smaller, it's lighter, it's cheaper, it's better in so many ways. Now we are using that on some marine applications, but what we found as we get into marine projects is that there are special needs for the marine sector. And on the bottom line, you see the FC Wave. This is really our premier product for the marine sector. It's a 200 kilowatt building block. And in the next slide, my third slide there, you can see what she looks like. It's a big refrigerator. So essentially it looks like a big electrical cabinet with all the interfacing put down in a common area for ease of installation. Basically, you provide this thing with filtered air, you give it a coolant connection, and you connect your electrical connections and your communications, and that's about it. And you get the benefit of what we've adapted from all of our experience of really over 4 decades of producing these things for transportation. In the next slide, slide number 4, you'll see how these things go together. You can put these things in parallel for a megawatt or more, and that makes it very conformable for different types of maritime vessels. You put together all these things on common manifolds, and you feed your gas and move your air around. And it makes for an adaptable solution that also is highly serviceable and something that electrical mechanics should be very comfortable in servicing. In the next slide, slide number 5, you can see how an integrated vessel would look. It's a bit of an eye chart. I apologize if that's hard to see, but essentially you've got a hybrid drive system. This is the same kind of electric hybrid drive system that we put on land-based uses. You've got hydrogen storage on the right. And in the case of marine vessels, there's a lot to talk about even for types of hydrogen fuel. Compressed hydrogen fuel has been popular for trucks and buses. That tends to get them to the kind of range and capacity that they need, but you can compress this element even further. This is the lightest and most compressible element known in the universe, and you can compress it to the point where it becomes liquid, and it becomes highly dense at that point. It's a cryogenic fluid, like LNG, as we talked about earlier. And you can also do a variety of other carriers that are being looked at, such as ammonia and other liquid organic carriers. Lots of interesting projects now looking at those sort of applications. So that gas allows you to put in the kind of capacity that you need. The fuel cells right next to it, you select for the kind of power that you want out of those fuel cells. Those need to provide the average power that your vessel is going to require. Your peak power is supplemented by adding in batteries. That makes this a hybrid boat. And you can see just to the left of that, on the other side of the power management, a bank of batteries. And putting those two technologies together give you a more economic and more flexible solution for achieving the kind of performance that you need for an electric drive system. This is an electric drive system, and all of that can drive the electric engine. So a boat that has been designed around batteries for battery electric drive, that design can be readily adapted to taking out most of those batteries and putting in fuel cells and then putting in hydrogen storage to reach the kind of range and capacity that you need to hit your operating duty cycles. In the next slide, slide number 6, some examples of projects that are already underway. As Dave mentioned, Europe is really leaping into this. We've seen a lot of activity, particularly on inland waterways. We've got some ferries that are underway in Norway, also up in Scotland and the Orkney Islands, and we've got some workboats out in Germany and in France, as Dave mentioned, that ABB project for a river barge there, and also working at the much larger scale for that auxiliary power system that Dave mentioned for cruise ships. So lots of activity in Europe to get these into the water. These ships are taking a variety of approaches. They're using both our motive modules, those 100 kilowatt modules, and they're also using the new FC Wave in applications going up to approaching a megawatt, getting close to that, and using a variety of fuel flavors. Some are using compressed hydrogen, and some are going to use liquefied hydrogen as well. In the US, we are thinking big. And on the next slide, slide number 7, here is that HyZet tug, the hydrogen zero emission tugboat that we're working on with ABB and Chart Industries, Crowley and Jensen, and a host of other notable partners. This is a study that is developing a design that's going to be ready for manufacture of a hydrogen powered tugboat, a multi-megawatt drive system. What makes this possible and what makes hydrogen necessary is that you can set the power that you need by the battery and fuel cell size, but you can then get the range that you need from the fuel. And we're looking at liquid hydrogen as an application for this to allow a week of operation in between fueling. This is going to be a 6,700 horsepower electric drive. And we accomplish that with a combination of 1.2 megawatts of fuel cell and 3.6 megawatt hours of energy storage system of batteries. And as I mentioned, liquid hydrogen, fuel storage, and bunkering. So we'll be doing a lot to open up the frontier for moving fuel onto this boat. We're showing the kind of range and operating needs that it has. Now, if you imagine that you tried to do this boat as all battery, if you're trying to get something like 40 megawatt hours or more of batteries on it, even assuming that you could, if you want to replenish this vessel in, let's say, 4 hours, you're going to need 10 megawatts or more of a charger connection. So the shore power gets complicated, the place to put the batteries gets complicated, and hydrogen helps to eliminate those problems and to allow for the kind of operational flexibility that you really need in the maritime application. So we're really excited to partner up with ABB for this and to start demonstrating really the large scale promise that hydrogen can provide for zero emissions at maritime ocean going applications. And with that, I'll click to my last slide for my contact info, and thank you very much for your attention and look forward to your questions.
Thanks, Tim. I'm going to do a real quick conclusion then. Again, what we're trying to do is give you guys, as you're making decisions on your large purchases coming up for your companies. This doesn't apply just to towboats. If you're doing dredge equipment, if you're doing tugs, you're doing ferries, anything that's going to be consuming fuel and producing power, electrification is going to be something that, as Dave says, future-proofs your design. We don't know what's going to be available 5 years from now, 10 years from now, 30 years from now, but your vessels are still going to be on the water. As I've joked with some of you guys have come by today, in 30 years, we may finally have the Mr. Fusion from Back to the Future, where you're able to throw garbage in and it's going to create electricity. We don't know what's going to be out there yet. What we do know is what we have now: LNG, diesel, hydrogen, potentially ammonia, fuels like that. And we can partner those with electrification. So if you want to use a bridge such as LNG to help reduce your emissions, you can couple that with an LNG engine that is a generator, coupled with an electric drive and energy storage, and you can get to that. And then 10, 20 years from now, when you decide to repower and fuel cells are something you're interested in, you pull the engines out, you can put the fuel cells in, your boat's going to be the same. How it behaves will be the same. You've just now repowered it into something that's cleaner and more efficient than before. And that's like an exciting thing I see on the fuel cells is they are massively more efficient on the fuel they burn to the power that they actually provide. So with that, actually, I'm going to kind of open it up to the questions. The goal of this is to ask for you guys to ask. Tim, I'm going to start the question with you on one is compared to a normal diesel internal combustion engine, what is the efficiency gain of the fuel cell for that? What's a good comparison?
We're about 2x based on our land applications and the buses that we're seeing on the road. We're a little bit better than 2x for CNG and right around that for some of the hybrid diesel applications. So we get about twice as far per unit energy.
And so that's why, these are the things that are coming and it'll be there. Does anyone have any questions for any of the panelists? Nothing? Mr. Stone? Tim, so the question is, because I had to repeat it for Tim only because he's not able to hear the mic. So Tim, the question is infrastructure, particularly with hydrogen for marine applications.
Yeah, it's emergent. There's a few different approaches that are being looked at right now. Some folks are looking at moving fuel pods or cubes out. Each of these cubes hold a number of compressed gas cylinders for compressed hydrogen. That's pretty impressive, but they are rapidly advancing cryogenic fueling for hydrogen based on, largely LNG experiences. So there's a company, for example, called Tokyo Becky that's doing it for shipment of hydrogen out of Australia up to Japan. So they're highly motivated to make these. You may have seen the announcement of a Kawasaki hydrogen freighter to move that fuel back and forth. So it's emergent, it's coming. It's not out there today, but it should be getting tried out over the next couple of years.
And Josh.
And go ahead.
This one. All right. Oh, all right. So the other thing to understand about hydrogen, it's also as well a stepped change, right? That step change goes all the way into incorporating offshore wind, where we finally get to green hydrogen. What we're talking about today is a lot of gray, that we still use fossil fuels to create the hydrogen. One of the projects that we're working on internally at ABB is utilizing methanol as a fuel on the ship and having an on-ship reformer to take that methanol and turn it into hydrogen. Methanol, I mean, you guys, if you're an inland carrier, is something you carry every single day. It's a liquid, right? You can easily replace fuel tanks at that point versus going to cylindrical high pressure tanks, but you can do the reforming right there on the ship. That's still not green hydrogen. It's much more green than what we're doing today, but it's that stepped approach that we have to take to get there.
And on the LNG front, the infrastructure is rapidly developing right now. The oil majors are finally, they're really starting to step up and support that initiative. So we are seeing an expansion of the infrastructure, particularly in the key locations, things like Memphis, St. Louis, the Baton Rouge, Port of New Orleans area. We're seeing them make the investment on the marine side for that infrastructure. Because again, they're starting to see this is a potential market for them to provide their product for, provide their LNG for. So what is one of the big things that's been holding up LNG for a while is that marine infrastructure. It's coming. I think, again, because the technology between LNG and hydrogen, like Tim was saying, is so closely related on how you transport it and how you transfer it, that as that LNG infrastructure gets put in place, the hydrogen infrastructure is going to be very close behind it because it's almost exactly the same stuff. Any other? Yes, sir. Yeah. So Tim, I'll repeat it for you. So the question is, the automotive industry has already tried hydrogen at one point. And due to the lack of infrastructure, it sort of withered on the vine. And that's where the batteries and the current electric vehicles really kind of took off. How do you see this current push with hydrogen being different than approximately 20 years ago when, we did see like the hydrogen from Honda and all that?
Yeah, for sure. The batteries actually are largely responsible for the resurgence of hydrogen. Successive companies like Tesla really emboldened policymakers to go for things like zero or carbon neutrality mandates and the kind of funding that backed them up. And that allowed us to keep progressing. I mean, that whole time, Ballard's been improving its technology to get its prices down and to get its performance up. But there are still hydrogen passenger cars out there, but infrastructure really is a problem. But what people are seeing more and more is that hydrogen's role to complement those battery vehicles is actually in the heavy duty space for that larger energy capacity, that longer range. In the transit bus world, in California, they're required to go zero emission, and they had to show what they were going to do. And what we're seeing is that about a quarter to a half of all those buses are going to be hydrogen rather than battery because of those advantages. And because once you start getting fuel in centralized depots for fleets, it makes a heck of a lot of sense. That's the difference between hydrogen and batteries, or one of the differences is that you really want concentrated usage in one spot. The problem that we're going to see on the battery side, where hydrogen is going to be very welcomed in the very near future, is that right now, if you have a whole bunch of electric vehicles widely dispersed across the grid, it's not a problem. The grid can handle it. It's when you start putting a very large fleet, when you get beyond single digits of fleet penetration, and you start to have to upgrade substations and feeders and transmission lines in places where the grid's already taxed, and we're already dealing with variable renewable energy that require very large battery banks. When you start having to deal with different charging requirements, like a vessel pulling up and requiring 40 megawatt hours right now in the middle of the day or the middle of the night, that becomes problematic, and it becomes expensive to build a grid that can service that in a built up area, particularly at the ports. So we're developing hydrogen right now for large fleet applications and showing good success, but it's going to be very well appreciated once we start getting to levels of 25, 50% penetration of zero emission vehicles. And really it's that last 50%, 20% of electrification where hydrogen is really going to be needed to avoid making a very expensive, very complicated grid. And I encourage you to track and watch the cost of grid expansion and the projected cost, because it's not well understood and it's certainly not well advertised. And that's part of the value that hydrogen is providing. And now that we've hit economic cost, the cost of a 12-year cost of a fuel cell bus is within 2% of the 12-year cost of a battery electric bus. So we're there cost-wise, and we're there to complete that decarbonization picture that was just speculation only 15 years ago, and now is mandated, and people see it as necessary.
And I think another thing to remember though, so I'm not sure how many of the hydrogen cars were sold, maybe 1,000, 2,000 or so, and so you're talking about filling 2,000 tanks of 10 gallons each. We're talking about one towboat, if it was on a towboat, needing 150,000 gallons every 10 days. So there's a scale, and then all of a sudden now we're delivering tankers full of it that are going to go to the locations to fill the vessels up, or there's going to be bunkering vessels that, because of the scale, now it becomes viable to build some mobile infrastructure to get the fuel to its location, much like we're seeing with LNG. It took a long time. LNG boats came, with tote, and we were tasked with designing an LNG bunkering vessel. So we're bringing the LNG to those vessels. I pictured it much the same as hydrogen. Dave, did you have?
No, I think one of the big things here is it's a balance. And I think Tim talked about it before. Batteries are great, but you can only design an inland or a tug so far around batteries. When you have some of that sustained travel, so again, a battery fleet boat, okay, that makes sense. A battery assisted diesel electric makes sense. But if you start talking zero emission, you need to take that step to hydrogen to get that sustained travel along with the battery to back it up for those real tough demands and peaks and depths. So.
And I just want to make one thing kind of clear so everyone understands, like, so no one up here, we are not battery salesmen. So we bring this as part of how we believe in integrating a full solution for your products, whether it be fuel cells, LNG, some type of electrification. So we're here, we're not pro battery because we're trying to sell you batteries. You guys don't have batteries to sell. I don't have batteries to sell. Tim doesn't have battery cells, but we understand its integration into the technology is vital along with these other steps along the way. That's why we want to make, this is an information session for you guys to ask, what I think of the experts in this area, especially on the inland side where people have that focus. When you've got that experience, we know what the inland operators are facing. So with that, yes, sir, in the back there. Dave, I'll let you handle. So the question is, what's the reliability of the systems? So I'm going to break it up into two parts. First one, Dave, will be, I want you to go over the electric, especially like the DC grid style. Yeah. And then Tim, I'll turn that over to the second part will be fuel cells on reliability. So David.
Yeah. So first thing first, I think a lot of you out there know I'm an old towboat guy. I'm a mechanical engineer. I love things that make a lot of noise, that create a lot of heat, that just gives you raw power. I used to do truck pulling. That's one of the coolest things in the world, just that amount of power you have. Also, at the same time, it's amazing what we did there. We have engines that have explosions inside and they create power. Explosions, we've tried to make it as predictable as possible, but it's still an explosion. And I know all my engine guys out here in the crowd, there's set regiments on when to do maintenance because it's a good guess of when something could fail. An electrical piece of equipment, for instance, an electrical motor. I was in chemical plant for 10 years. I was over maintenance. It just runs. It has two bearings, a stator, and windings, right? And it wants to run. And there's no true mechanical interface other than those bearings. Same thing on the internals of the electrical. The biggest thing we always had to work on is the actual forks that are inside that get worked all the time. You can check that through easy thermographic analysis. So it really starts changing the game at this point to a more predictive analysis on how you can do the maintenance side. I mean, we have drives in service 30, 40 years. That just, if you do the preventive maintenance, which a lot of times are filters, some cards, a few different things, it's much, much more reliable than what we're used to today.
Tim?
Yeah, so the reduction of the number of components is definitely something to look at. A diesel engine actually has a surprising number of components that have been pretty standardized these days. On the fuel cell side, we've got a pretty limited number of components. The stack itself, we've progressed quite far, 20 to 30,000 hours between rebuilds, and that's a block that you take out and you replace. You send it back to the factory and we rebuild all the cells for you and send you back a new unit. Even the balance of plant components like the blowers, our air compressors now are non-contact. They're air bearings. So again, they just spin and they run, and now they're lasting as long as the stacks too. So maintenance gets to be quite easy. It's verifying that sensors are still working and then replacing basically air filters and checking cooling conductivity. It's pretty straightforward. The main thing is to get your mechanics and technicians up to speed and comfortable working on high voltage and compressed gas. And once you're there, it gets quite easy. Get familiar with laptop diagnostics and you're good to go.
Yeah. And from my end, I was a old port engineer in the Coast Guard, naval engineer. So I served on ships as well, big opposing piston, Fairbanks, or gas turbines. And when you take a look at maintenance and reliability, one of the biggest goals is to reduce the number of rotating parts. How many moving parts do you have? Because that's what breaks, that's what wears out. And when you take a look at the fuel cell, the only moving part, and correct me if I'm wrong, is fans and the fuel pumps, liquid pumps. There are no moving internals. Same thing for an electric drive for the motor itself. You've got the one rotating part. You don't have 16 cylinders with 32 valves and how many main bearings are getting worn in. All these things are part of maintenance. And by reducing the number of rotating parts, the number of parts that are in friction with one another, you're going to reduce your maintenance and you're going to improve your reliability. Heat is another one. Engines are hot because as Dave was saying, you're controlling an explosion. Explosions are reduced efficiency, but you're also now putting that heat into products. Things like fuel cells, where they're very low heat, you're not putting that stress into the components to contain the heat anymore. So again, that in general, from a theoretical standpoint, will always improve your reliability. And so I got one last question. Did you have one? All right. So the question is, is where, and it's a good, very valid question. And the question is where does that leave people who've just built new boats, met tier 4? You've made this investment, and you're right there. That's a very tough question. You're taking a look at what you've got on board and what you're going to, how to get through the future. I think as you go into the future, what you're going to look at is when you come up to your next repower, or you need to do, you need to pull your engines out and you're going to put something new in, is you take a step back and go, okay, what should I do at this stage at year 10, year 15, year 20, and start saying, how do I future-proof my vessel for the next 30 years or 40 years? All these technologies, be it fuel cell, electric drive, LNG, as we have shown. I know that you guys have done a number of retrofits. We're retrofitting LNG on existing vessels. I mean, one of the vessels we're putting LNG on, the vessel is 40 years old. These technologies can all be put into place in some way, shape, or form, whether it be through PTI, PTOs, through gearboxes, do mechanical hybrid gears. As soon as you electrify, now you can start looking at things like fuel cells and other technologies that are out there. So I would say what it's going to do is delay the implementation, but it's not going to say it's never worth it. At some point, again, when you get to that repower stage, talk to people, talk to the experts to say, does this make sense for me at this point in time on these vessels? Should we make the investment going forward, or do we keep what we have? The landscape's gonna be different in 10 years. The batteries are gonna be different. The fuel cells are gonna be, the motors are gonna be different. Everything's gonna be different in 10 years. Make the assessment when it makes sense for you guys to do that. And Dave?
Yeah, I have something to add. I mean, anybody who's decided to go tier 4, I mean, you can just look at the past tier 0, 1, 2, 3, and how the EPA has looked at those, right? And that's immediately when I say that EPA, then my decision is in their hands. And if you can tell me what the EPA is going to do in the next 10 years, then I'm going to give you $100 today. Okay. So that's where I was at a conference in 2019 talking about inland and tug. And one of the guys came from the EPA. These boats last so damn long. And from the EPA standpoint, they had a projection where we were going to be by 2050. They completely underestimated how long these vessels are around. So that estimate is way higher. And with that, one of the questions from the audience came up, is forced retirement ever going to come around? And the individual on the panel said it's always around to try to get to those end goals. So if you did go that route, what I can tell you is your decision is in the hand of the EPA for the next 30, 40 years, however long that vessel lasts, right? And that's, I guess, pretty much exactly what Josh is trying to say. If you do go electric, you can change out that power plant behind, where if you go on tier 4, you're with a diesel engine, you're with urea, you're with the dosing cabinets and everything that comes with it. Okay.
Yeah, but it's not going to keep you from ever making that investment and making that change at the end of the day. So I think our time is up. So if any, we'll be sticking around. I know we're all around. And if you have any questions for us, and we can also send any questions to Tim. We do appreciate your time. Thank you very much. And have a good show. Like Dave says, good to see everyone again.
Thank you all.
Thanks, everyone.